How do we solve a problem like this? What is the area of the region in the first quadrant bounded by the graph of y equals e to the x over 2 and the line x equals 2? I'm going to tell you, it's nothing new. This is what we've been doing for a little while now. So what I want you to do for all 4 of the problems on this handout here, I want you to actually try all of these problems yourself. See if you can figure them out. Maybe sketch the graph, maybe do some calculations. See if you can figure them out yourself. Okay? Before we go through the solutions. All right. Hopefully you've at least tried or thought about the problems. Let's try example 1 together. What's the area of the region in the first quadrant bounded by this function and the line x equals 2? Well, we know y equals e to the x over 2 is just an exponential, right? Another way of saying this is e to the 1/2 x. So it's just like a regular exponential, but it's been, transformed a little bit. But it's gonna, have the same rough shape as our regular exponential function. And the line x equals 2. So the line x equals 2, we know x equals 2 is a vertical line, right? At x equals 2. I'll label this one 2, y equals e to the 1/2 x. Okay? So it's saying the area in the first quadrant bounded by that. So if you look, there's sort of those two functions create this area here in the first quadrant, right? It creates this area in here. And this problem is asking us to find what that area is. Well, we know how to find areas, right? We know that the area is just going to be the integral, right? It's going to be the integral of this function here between 0 and 2, right? And that's all there is to it. There's nothing else to this question. That's all there is to it. So the area in question, if we call this area A, area in question is just going to be the integral from 0 to 2 of e to the 1/2 x dx. Now, we can evaluate that using whatever means you want, but I'm just going to tell you the answer here is approximately 3.437. So you can solve for that in whatever way you want, but I'm gonna give you the answer. All right. So the only complicated thing about this problem, the only difference is that instead of telling us to find the area between 0 and 2, it's telling us to find the area between these two functions. I mean that technically x equals 2 is not a function, but it's telling us to find the area between these two relations. So you have to interpret that yourself to know that it's between 0 and 2. And you'll see that's the pattern with the rest of the questions too. It doesn't tell you what boundaries to establish. You have to figure out based on the problem what boundaries to establish. Determine the finite area enclosed by x squared and y equals root x. Well, we know these functions. We've been dealing with these functions for a long time. So I'm going to start with a roughly accurate sketch of these functions. So we know we know x squared is going to look something like this, right? 1, 2, 4. It's going to go through those points. I'm going to try to draw it roughly accurately, just so we can really understand the problem. Like that. And then root x, we know starts at 0, 0. It goes through 1, 1. It goes through 4, 2. And because it's basically the inverse, right? So then we can sketch that like that, right? And we'll just stick with the positive root here. We'll assume it's a function. So if this is the case, what's this area asking for? What does it mean by finite area enclosed by those two graphs? Well, enclosed means between those two functions. It's like they surround it, right? And finite area means the area that's finite, the area that's not infinite, right? So if we notice the area between those two curves, there's a little piece down here, and then there's this piece here. And this is the infinite piece, right? This goes on forever if you keep going with these lines. So it wants the finite area. So basically it's asking, what's the area of this little sliver in here? Right? So we can zoom in down here. I'm going to color that in like that. We want to find that area, right? Now, how are we going to do that? Well, first of all, we notice these two graphs intersect at, these two graphs intersect at 1, 1, right? So this is between 0 and 1. So we're only really looking at these two functions between 0 and 1. And if we wanted to find this area here, what could we do? Well, we know that this one is going to give us the bigger area, right? The red function is going to give us the bigger area. And if we find that, it's going to give us, oops, let me put on my highlighter. If we find the red area, it's going to give us this area like right here, right? So it's going to give us this big red area here. And then if we wanted to figure out what that sliver is, we need to subtract the area below, which is the blue area here, right? So essentially, if we could find the red area, subtract the blue area, we're going to be left with that sliver there, right? So we can let's call the red area A. Oops. Switch back to this. Let's call the red area A, big A, and that's the whole area for this whole thing. Let's call the blue area A2. We'll call it A1 and A2. Let's do that. A1 and A2. And then the final area, the area of that sliver that we want, we'll call that A3. Or you know what, let's just call that A, and I'll highlight that in green. So we want A, okay? So I know it's in that tiny corner of the graph, and there's a lot happening down there, but you know, what we're essentially trying to do is that A is going to equal A1 minus A2, right? So we need to find what A1 and A2 are. Well, as we said, we know that A1 is just the integral between 0 and 1, right? So we can actually just substitute this in. A1 is the integral between 0 and 1 of the function that's on top, right? The bigger one. So that's root x dx. And what we're going to do is we're going to subtract from that the integral from 0 to 1 of A2, or of x squared dx between 0 and 1. And that's going to give us our total area. So this is something we can just plug in to Desmos or any other graphing software. And sort of interestingly enough, if you do this, you'll find that the areas come out actually rather nice. The red area comes out to 2/3. The blue area comes out to 1/3. Sort of cool that these, somewhat complicated looking shapes actually have very simple areas when you find them. And if you do the math, obviously, the area is 1/3. So sort of interesting that this sort of breaks up the area into 3 chunks. If you really think about it, right? It's basically saying that like this is 1/3 of the area, this is 1/3 of the area, and then up here, which we didn't care about, is also 1/3 of the area of that 1 by 1 square. So sort of interesting. So let's go on to the next question. We'll see if we can make this a little bit more complicated for you. Again, I encourage you to try these all yourself before we go through it. It's, that's how you actually learn. So we're asked here to determine the finite area enclosed by 2x squared plus 10 and 4x plus 6. So those are two functions. One's a quadratic, one's linear. And x equals -2 and x equals 5. Okay, interesting. So I'm going to start off by just graphing x equals -2 and x equals 5 because those are really easy, right? So -2, x equals -2 looks like this, right? X equals -2. X equals 5 looks like this. So we know that those are probably going to be sort of the boundaries of our integral, right? Now we have the other ones, 4x plus 16 and 2x squared plus 10. And you notice that these have big numbers involved, so the scale of 1 isn't going to really work here. I set this to 0, 1, 2, 3, 4. Let's not worry about the vertical scale so much. So I'm not going to do it to just to accurate because the y-intercept is 16 of this one. So, but we know it's roughly a line, right? So it's going to be something with a positive slope. So it's going to be something like this, right? Y equals 4x plus 16. And then the other one's a parabola that opens up, and the y-intercept is 10, right? It's got if you set x to 0, the y-intercept is 10. So that's going to look something, I don't know, it's going to look something like this or something. I don't know exactly what it's going to look like, so I'm just going to sort of roughly sketch it. Okay? I don't know what it's going to look like. So the question is, how do we do this? So first of all, we want to find the area enclosed by those two. So in other words, we want to find the area between those things. So for example, this is part of that, but then this is also part of that, right? And also this is part of it, because it's between all those things. So there's basically 3 regions we need to find the area of. So this gets a little bit more complicated. So I'm going to call this A1, I'm going to call this A2, and I'm going to call this A3. So how do we do this? Well, first of all, I think we need to identify where these things intersect, because so it changes it, right? In this case, we have this function on top and this function on the bottom. But then it switches. Then we have the linear function on top and the parabolic function on the bottom. So we need to, in order to take the integral, we need to sort of know which one is on the top, which one is on the bottom, to know which one to subtract. So let's start off by finding the point of intersection between these two functions, right? Because the point of intersection is going to be here and here. So to find the point of intersection, we just set the equations equal to each other, right? 2x squared plus 10. So this is to find the POIs, by the way. 2x plus x squared plus 10 equals 4x plus 16. And we can just solve this. 0 equals negative 2x squared plus 4x plus 6. And we can solve that, in a few ways, but we can just solve it by factoring. If we factor out a negative 2x squared plus, minus 2x minus 3. And then we see it's negative 2x minus, what is it going to be? X minus 3, x plus 1, right? So the points of intersection are x equals 3, and x equals negative 1, right? So when I sketched it, not too bad. A little bit off with this point of intersection over here. So this should actually be 3, and I'm going to cheat. I'm going to change that to be 3, so I know it's not spaced evenly. But I put that one at 1 already, so that's fine. So these are at 1 and 3, those points of intersection. So when we integrate, we should do 3 separate integrals, basically, right? So to integrate the first part, we can do the integral of, to find a1, the integral is going to equal from negative 2 to negative 1, right? So just that first little piece. And that's going to be the quadratic over the linear one, right? So the quadratic, we're going to subtract the quadratic. So this is going to be 2x squared plus 10. Now, I could do it as 2 separate integrals, but we could also realize we're integrating with the same upper and lower bound. So I can actually do it all as part of one integral. And I'm going to subtract 4x plus 16. See? Dx. So the advantage of this is that if I were to plug this into some software to figure out the integral, it's all one integral, so you don't have to keep on writing all the separate integrals. And we could do the same thing for a2, except this one's going to be between negative 1 and 3, right? And it's going to be the same function, so 2x squared plus 10 minus, not the same functions, my bad. In this case, the linear one is on top. So we need to put that one first, right? 4x plus 16, or else we'll end up subtracting from our answer, which is not what we want to do. We want to add to our answer, right? 2x squared plus 10 dx. And then our a3, the quadratic is back on the top, and that's between 3 and 5, right? So that's going to be 2x squared plus 10 minus 4x plus 16 dx. Don't forget about the dx. Oops, dx. So if we do this whole calculation, we end up getting that the first part is 14 over 3 exactly. The second one ends up being 64 over 3. And the third one ends up being 64 over 3 as well. Sort of interesting that these complicated things come out to nice fractions. So the total area enclosed by the functions are 14 plus 64 plus 64, 142 over 3. Okay? Or as a decimal, it comes out to approximately what does it come out to? 47.33. Oops. 47.333. Okay? So when the lines cross, we have to be careful to include them as separate integrals because we don't want to end up subtracting our numbers. If we didn't do that, we'd end up doing this minus this plus this, which isn't what we want. We want to add up the three areas, right? Okay, then we have our last question here. Determine the area bounded by x equals negative y squared plus 10 and x equals y minus 2 squared. Now, you might be thinking, what does this look like? And we're going to do this one actually without graphing. We'll graph it at the end to see what it looks like, but, if we don't know, let's just try to figure it out. And you probably could graph it if you really wanted to, but let's just do it as if we don't know. So, the first thing we should do maybe is find our points of intersection, because that's going to determine the areas, the points where those two lines meet, and it's going to determine what the boundaries are to our integral, right? So we can set these two equal to each other. Even though we're not setting them equal to the y equal to each other, we can still solve it like this, right? Y minus 2 squared. So if we distribute this, y squared minus 4y plus 4, and this side we have negative y squared plus 10. We can simplify, so 0 equals 2y squared minus 4y minus 6, right? And then again, we can factor and simplify, so 2y squared minus 2y minus 3. So our zeros of this equation, or the points of intersection, is going to happen when y equals, what is it going to be? It's the same as before, isn't it? Y minus 3, y plus 1. So it's going to happen at y equals 3 and y equals negative 1. So the thing is, we could look at this and we can say, hey, can we, find out the x coordinate of those points and do the integral between that? Or we could just realize, hey, why don't we just work with the y, since the y is a thing we're given anyways. And we can take the derivative or the integral with respect to y or with respect to x, and it doesn't matter. It's like we're just flipping the axes, right? It's the same process. So essentially what I know is to find the area between these two. I think it's safe to say that it's going to be between negative 1 and 3, right, of the two functions. Now, we don't know which one is on top. So that's, we can do a little test to see which one is on top, which one to do first. And the easiest way to do that is plug in a number between 3 and negative 1. So which one is the larger value? So let's just plug in a 0 here and a 0 here and see what we get for y. Here we get x equals 10, and here we get x equals negative 2 squared is 4. So clearly, it means that this function is a larger value, right? So in other words, if you were to graph it, it's going to be on top. So we should do this one first. That makes sense, right? So we're going to do negative y squared plus 10, and I'll do this inside separate brackets. We'll do it all in one integral again. Minus y minus 2 squared dy, because y is our variable of integration this time, right? So if we do this, what are we going to get? Let's just throw that into Desmos. And if we do that, we end up getting the exact answer actually is 64 over 3. That number likes coming up in these questions. Okay, so you see it's 64 over 3. Now, is that the answer? Are we good with it? Well, I think we did everything right, but let's just check to see what's going on. Let's do a quick sketch of what's going on to see if this is an answer that makes sense. So I'm gonna continue to call this x and call this y. Now, if you notice this is, if we were to isolate for y in order to graph it, it's going to be a square root function, right? So this, our first function, is going to be y equals the square root of, what is it going to be, 10 minus x, right? Or negative x minus 10, whichever way you want to think about it. And if you think about what that's going to look like, that's going to be a square root function that's sort of transformed to the right by 10 and then reflected in the x or the y axis. So it's going to look something like this, right? But when we took the square root of both sides, we actually should consider the positive and negative root, right? As we always do when we take the square root of both sides. So this actually has a negative root too. It's basically the inverse of a parabola. So interesting. It's not a function, but we were able to get an answer for it. So the next part, x equals y minus 2 squared, if we were to isolate for x in that case, we'd end up with y equals plus or minus, what's it going to be? The square root of x, and then plus 2, right? So what that's going to look like, it's just going to look like a square root function that's transformed up 2. So it's going to look something like this. I didn't really draw it to scale, but something like this. Okay? So the area bounded by these two, as you can see it, is this area in here, right? So, I mean, did we do it correct? Well, you might say, no, the blue function is on the top here, and then the red function is on the bottom, and then the blue function is on the top, and the red function is on the bottom. But remember, we didn't integrate it with respect to x. We integrated it with respect to y. So essentially what we did is we turned the page so that our x is like our new y. So we're looking at it actually in terms of subtracting the values going this way, right? So if you think about it, like this is the new up direction. If you turn your screen, if you turn it so that that's the upwards direction, you can see that the blue function is always the one that's bigger than the red function, which makes sense. So in this case, it actually made it a lot easier to use y as our variable of integration than x, because if x was our variable of integration, we'd need to do separate integrals for this part and then this part here. Do you see that? But we ended up getting the right answer. So just keep that in mind. If you're given something in terms of x, stick with that. Stick with y as your variable of integration. You don't always need to make things explicit in terms of y. All right? There we go.